So that's the advertising, and what we're going to hear in the next 3 hours will be some of the meat, the substance behind all of that through a series of presentations and panels. I'm Roland Pease. I'm here to try and make things run smoothly while we do this. I'm here for two reasons. First, as a science journalist, I've been to Culham many times to see its operations, to see the experiments. I've been to other places like ITER as well. Another reason, though, is that I feel like I'm a twin of fusion research in the UK. If people who complain about how long it takes to get to fusion, I'm actually in the foremost, because I was born alongside Zeta, not far from here, just over the hill from Harwell. I used to come and sit in this hall and watch children's entertainments, I think put on by the Staff Association, Christmas parties and all sorts here. I was at boarding school while JET was being agreed, and then they started to build it. When NET designs were being started, I was actually, I need the quote here, I was actually at Nature in 1991 when the first deuterium reactions were done at JET, and I wrote an editorial which ended, unless those working on controlled fusion can pull something out of a hat, there may be a shortage of milestones in the next few years. So this is, for me, very much a personal as well as a professional journey, watching what's happening here. I've been reading as much as I can of the Royal Society documents, the papers which have been put together for STEP. I find them absolutely energizing. I'm really quite thrilled by the scale of ambition that seems to be represented here. So that's what we're going to dig into in the next 3 hours. But first of all, let me introduce Sir Chapman, who's the CEO, please come forward, a CEO of UKAEA. I don't think you'll need any introduction in here. There may be some people outside who do, but I would say that essentially you have been running the gestation of STEP, and in a couple of months you're about to see it go forth into the world. Let's hear more about it, Ian.
Yes, that's right. It's like watching one of your children grow up. So you'll have noticed that we didn't have Brian Cox or David Attenborough doing the voiceover, but the price was right. So the kind of the fact that you're either in this room or you've joined the webinar, I think already that means you're interested in fusion energy. It probably means that you already know about all the upside of fusion, the opportunity to provide sustainable, low land use, low carbon, continuous energy. As Roland said, today we're going to talk about some of the things that make that noble goal, and it is a noble goal, a fiendishly difficult goal. Fundamentally, fusion is really hard. Delivering fusion power is a complex, massively integrated problem. One where it is highly unlikely that there will be some sort of magic bullet or single breakthrough innovation. Instead, it's just one where you have to do a lot of hard graft. You know, thorough science, detailed engineering, and even then, you have to carry a high risk appetite to make real progress. The only project anywhere in the world today that's building something on fusion plant scale is not STEP. We're not at that stage. It's ITER. It's the only one. And the community is finding, in spades, that delivering a project like that is really tough. There are lots of geopolitical reasons that ITER is tough, but it's also technically tough. And ITER is well behind schedule and well over its original budget because it's hard. But, I should be clear, ITER remains tremendously important for global fusion. It's already establishing supply chains that just didn't exist before. It's providing a huge amount of learning that other prototype power plant projects can build upon. And STEP is one of those projects. The initial thesis that we had behind the STEP programme, which began 5 prime ministers ago, which sounds like a long time, but in British politics, sadly not, a few months, was to target a prototype power plant that could be that opened a pathway to being smaller than the ITER variant might be, and so aim to have a lower capital cost. So right at the core, at the heart of the program, is the notion that it's no good just to deliver a fusion plant that produces power. It's not the end game here. The aim is to target a fusion plant that produces power that someone will buy. And if you don't do that, you have a product that has no market. So it's super, super important. Look, for sure, whichever variant of fusion turns out to be the most attractive, they are all capitally intense projects, right? They will require a lot of money. Fusion is undoubtedly capitally intense. And the cost to the consumer, and we need consumers or it's all for naught, the cost to the consumer is dominated by the overnight costs, the capital you have to put up front, and then how much of the time the plant operates. So if you have a huge bill up front and then you operate for 10%, nobody's buying that, right? So we set ourselves a target. The project had at its thesis a power plant architecture trying to minimize the overnight costs at an acceptable technical risk, that's already a trade, and make maintenance as easy as possible so that you maximize the availability. Like I said at the start, fusion is this massively integrated problem. I think it's very unlikely there'll be one design which is just way better than all the others, or one single innovation that transforms the field. That's precisely because it is an integrated problem. So with STEP, we're targeting as small a size as we can achieve for acceptable technical risk. And as I say, that sentence itself belies a huge amount of trade-off, and easier maintenance, amongst other things. Those properties are great in many ways, right? It's good to aim for that. But they necessarily drive challenges in other areas. So, for instance, it makes it much harder for us to be fuel self-sufficient. It just does. We know that that's a trade-off. So we're driving a challenge somewhere else. You know, there are lots of other ventures in fusion, lots of people trying to do this a different way. They target different designs. All of them have their own advantages, undoubtedly. They have advantages, and the proponents will tell you until you don't want to listen anymore. They'll keep telling you about the advantages, but they all come with commensurate disadvantages. And the proponents don't often talk about that, or maybe even know about that. Which will be the best? I get asked this all the time by investors. Which of these technologies is going to end up winning? I have no idea. And anybody that tells you that they know is lying. Ultimately, it will come down to who engineers the best product. Who has a product that costs the least and runs the most and the consumer wants to buy. You know, in the way that in combined gas turbines, there were literally dozens, probably hundreds of entrants at the start of the market, and now, you know, General Electric, Mitsubishi, Siemens, they dominate the field because they have the best engineered product. So to really, truly actually make some progress, you just have to stop talking about the advantages and extolling the virtue of your concept and just knuckle down and do the work. Actually get into the detail. And only by sweating the details of any design do you really learn about the challenges that you face. And that is what we are doing. We are now a team of about 1,600 people working on STEP. 500 different companies involved. It is a national endeavour. This is 5 years of detailed, dedicated work that has led to a concept design that we're reporting here collectively for the first time. You know, actually, since we wrote the papers, the design has moved on. It has evolved still, and it will continue to evolve over the next few years. So this is just a snapshot in time, and it is already slightly out of date. I finished by saying I'm very thankful to the Royal Society for publishing a special issue in Philosophical Transactions about STEP, and especially to the guest editors, Steve Cowley and Howard Wilson, for their hard work in leading the review of all of those technical papers. PhilTrans is the world's first and the longest running scientific journal. It has published a list of totemic scientific progress over centuries, really centuries. So it felt an absolutely fitting place for a compendium on a project that might, just might, join that list. Thank you.
Thank you, Ian. And to follow some proper detail from Chris Waldon, who's the chief engineer of STEP, and now we'll really get into the nuts and bolts, I hope.
Thank you very much. So good afternoon, everyone. My name's Chris Waldon, and I'm the STEP chief engineer. I've been on the programme since the very beginning, when it was a twinkle in the eye, and it's easy to be dazzled by the pioneering programme and pioneering mission, but at its core, it's a human endeavour. People deliver programmes, and many of the authors, co-authors and supporting a team have been on a journey into the unknown. All of these individual journeys are entirely necessary but insufficient. You can't get there alone, and it's about the collective. So to use a football cliche, I can see Ian's going to groan at this, but a team of champions doesn't necessarily deliver a championship team. But for those that are brave enough to step onto the pitch, it's about using ingenuity and to seek out those opportunities. Build skills through working through difficult, diverse challenges together towards a common goal. The performance of that original JET team has inspired generations within the community, and JET's legacy is the capability that was developed in the delivery and exploitation that continues to deliver major fusion programs to this day. So as a key take-home message, I want to say that the enduring value lies in the capability and knowledge that we develop as we work together to deliver our prototype fusion power plant. This is our legacy. But just like it was for that gang of 11 in the picture there, this is a big extrapolation from today's machines. Progress in this unknown space is hampered with doubt, flawed perfectionism. It is both complex and complicated, and the demands are going up and up and up. Increased performance, increased functionality, and it can be quite onerous. So thinking of other, I kind of reflect about where else can you see such a complex and complicated problem. And it makes you think about social design, it makes you think about health systems, for example. So here in the UK, in the NHS, they have this wonderful expression, which is the inverse care law. The harder you try, the further away those who most need the care become. So similarly, in fusion, we have concepts, but we put more detail into those concepts, and they're like mirages. They disappear in front of your eyes. So I do agree with Ian. The devil is in the detail, but so is our salvation. So, I'm about to embark into this unknown space. I need a North Star. And, for the team, it's about agreeing what that design brief is. And just like you do when you go out and think about, I'm going to get a new house, you can sit in isolation and write a list of all the things you want your house to have. But actually, the key challenge is about that gritty interface between what the program requirements are and what the machine can deliver. And you've got this rub and this friction, but you can theorize about it, but actually, when you're buying that house, it's about what you do going out into the marketplace and getting that feedback. And what you thought was really important, maybe it's not quite so important now. And it's bringing that to life. Coupled with, and Ian's made the point, and it's on the back of Paul's paper, some guiding principles. I'm about to embark in this space. What are those guiding principles? And equally, Ian's made the point, even the best technical solution is worthless if it's unaffordable and undeliverable. But you're going to have that tension all the time through the program. Equally, design for maintenance from the outset. We know it's a first of kind, we know it's going to change. Don't learn the same lessons of hindsight that we've learnt in the community. And when we're making choices, think about the line of sight to where we want to get to, not just answering an immediate need. So that commercial line of sight of where we want to get to. And I started off this process in a theoretical way, thinking about a hierarchy of needs. I started with the show starter, I'm going to point at Hendrick, plasma. Then I want to get power out. Then I want to be tritium self-sufficient. Then I want availability, and then I want cost. But it isn't quite like that snakes and ladder journey I'm describing. Different concepts have different attributes, and that was the difference that kind of then started to think about, so strategically, how do I embark on this journey? And what manner am I going to engage in this horrible, hostile space? So, putting together any strategy, I've learned this from Paul, diagnosis of the problem, set out a policy, and then set it out in a coherent action plan. And with any unsolved, complex, highly interdependent challenge, it's making that balance between exploration and tangible progress. And again, breaking the deadlock with that, it's about thinking about what are those starting points. So we thought about identifying design families, starting conceive concepts, and then you can start to get engaged with that market, like I described with the house, and get the feedback. So we went from, I have my compass, which is your value-led, and then as we started to decompose the design space into a series of design decisions, a decision tree, going from broad regional prospecting, narrowing it down to an envelope, and then narrowing it down to a design point. That sets the cadence, that sets the focus, that keeps us going. And then we explore the data-led aspect at the bottom, that prospecting as we navigate across that space. So that was our strategy of engaging it. I think some of you have seen this diagram before, and it just so happened we had a pandemic. So the program, with all our makeshift offices set up in at home, and I was trying to teach 3 kids as well at the same time. We started this prospecting and going from a technological surveying, and we used the concept maturity levels from Nasar, which is from this region, down to a design point, and started evolving designs. And it sounds a bit Frankenstein, but we had many different design families and starting points, and some of those guardrails on that funnel, which is your key characteristics, some of them crashed out of there. Others, we had nice attributes, and we stole features from one and glued it to another concept, which was short in that regard. And slowly but surely, we took this evolutionary approach. But again, it's taking Ian's point again, it's building capability through exercising the decision muscle and learning as we went. And it's about capturing that. You can see the numbers there. There are a significant amount of concepts that we iterated, learning and getting better as we went along. And what we captured was the know-how and the know-nots, which is really important. Slowly but surely, the tensions, the character of the problem we're grappling with emerges. So the conflicting requirements, and there's a careful balancing to do about how we actually size this machine and the key attributes that impact that sizing. And then underpinning that balancing act is the key critical technologies that underpin that fully integrated design. But the third dimension to integration is time. As I start to put greater fidelity on that design, things reveal themselves. As I start prototyping technologies, I learn things that I didn't know. So that space is very dynamic. And of course, I have to design a machine that performs on day one and the last day of operation. So understanding the character of the machine and how it ages is also a critical aspect to our design. And I guess this is me and my post-COVID mind. I think of the integrated concept as a pathogen, a virus, constant evolving and mutating. And our team, our STEP team, our collective team, is like the immune system, reacting, counteracting every time it mutates and changes. And it's about that building that capability and exercising that muscle. So we've got new theoretical ways that we're going to tackle the problem. You'll see in the materials paper, Amanda Quadling's paper, there's a design by fundamentals, which is a whole new approach to building design materials qualification. You'll see in our paper, and the digital paper, the digital workflows, so iterating, build, test, learn, rebuild, those cycles getting better and better and quicker. And then we had areas of focus where we channeled multidisciplinary teams on specific aspects, exercising a more integrated way of solving. It's not just the plasma physicists, but or the material scientists, or the engineers. It's a combination of all of those communities working together, striking serendipity, and finding solutions. And then equally, all with that is the culture we employed on the program. That culture, the psychological safety, exploring, failing, learning, getting better, and all of the additional aspects of that culture, having single focus, is another capability that we've built, and we are going to continue to build as our team grows and grows and grows. So, I end by saying again, my key message is the enduring value of the program is the capability and the knowledge we develop as we work together to deliver a prototype power plant.
Before you go, Chris.
Uh-oh.
Well, no, it's very interesting to hear all that. With this report that you've now put out, do you think you've got the right launch pad for us to get to a working step machine in 2040?
You know I was saying about that evolving virus. Yes, I do think
Yeah.
we've got the right capabilities, the right culture. We're thinking differently. Actually, quite often people glibly say that creativity exists just in the conceptual phase and then here in the deliveries. Actually, my experience of delivering major things is as it crystallizes and the constraints lock in, the creativity doesn't go away, it actually brings it out more and more and more. So you can see examples in Fusion, for example, NIF, its initial results weren't fantastic, but they went through an iteration and learned, and they achieved their goals. So again, it's that creativity.
Yeah, no, I mean, I got this sense that there's going to be these two paths as you design and improve the design, that equally the more science is going to come in, more engineering lessons in some of the materials and so on. And you'll just be sort of tossing the ball backwards and forwards.
So all the engineers out there and scientists, they always want to do better. So there's always a bit of a constant tension about you actually do have to lock things down and deliver things. But there will be a parallel program, I'm sure.
That's brilliant. Thank you very much, Chris. I sort of get the sense reading the papers that there are, essentially, there's almost 3 experiments. I don't know if this is fair, 3 experiments in parallel. One is in the plasma, the plasma physics and so on. One is in the power design, getting the power out into generating electricity. And then the third one is this concept of making it also a machine which will be a prototype for the kind of machine that will be used and maintained and so on. And it seems to me quite an ambitious program to do all that. So the idea is now we're going to have 3 panels, which I think will break down some of those thoughts. The first one is on the plasma. I believe, if I flick my fingers now, we will get Steve Cowley up on the screens. We also have somewhere in here Hendrick, Meyer, Hendrick, and Morten, Lennholm, and Damian King. I'm trusting you've got the programs in front of you, so you don't need to. I won't read out all the honorifics and so on here, but some of our experts there's Steve. Hello. I first met Steve out at Mast when you were upgrading it, halfway through upgrading it, I think. Steve, can you just, I suspect everyone here knows the essentials, but just bring us up to date with the spherical tokamak idea.
Well, I think the spherical tokamak is a very interesting sort of story because in the late 80s at Culham, there was a number of people thinking about how you could improve the performance of a fusion device. We have kind of a mainline diffusion. That's sort of the ITER design, right? And the European demo, and the Chinese are going along that design. And I think the concern here at Princeton and at Cullen was that while that'll probably get us to fusion, it won't get us to commercial fusion, because commercial fusion has to be something that people are willing to pay for because it's at a cost they're doing. And so in the late 80s, there was this this work using some of the codes, people like Tim Hender and others were working on, what would be the could we tweak the design? Could we change the design into something that was more compact, faster, cheaper, that kind of thing? And the results from the codes were that maybe we could, and that this would have a better utilization of the magnetic field. We have a parameter in plasma physics, which is the pressure in the plasma divided by the pressure in the magnetic field. It's called beta. And if that's high, you're utilizing the magnetic field extremely well. And spherical tokamaks do that. And at Cullen, a machine was built, which was called START. It's sort of almost thrown together out of spare parts. And it performed extremely well. Then here at Princeton, we said, wow, that's doing pretty well, and there'd been some calculations here and we built a machine called the National Spherical Tokamak Experiment, NSTX, and MAST was built at roughly the same time. Those machines actually indicated not only could you get high pressure inside this device, but actually the confinement, the time it takes. We have another parameter called the confinement time, the time it takes the heat to get out of the device. And if that time is really long, it holds its heat in for a long time, it makes getting to fusion easier. And if you can get fusion easier, then it makes all the engineering easier. And so the premise in the 2000s of these two machines, NSTX at Princeton and MAST at Cullen, started to suggest the performance in sphericals might allow us to build a smaller, cheaper, faster fusion reactor. The results from MAST upgrade recently indicate that that's probably true too, right? That we can make a smaller device, confine a plasma, and therefore make a more efficient fusion reactor and get to market easier, all those kind of things. Then coming out of that, I think, with Ian's leadership, Cullen has said, we should actually envisage what a reactor looks like, right? Based on this concept. The results from the experiments keep coming up with this, performance might be much better in these machines. So it's a story of sort of scientific success, then sort of indicating that there may be a route to fusion that really is more efficient, more. I don't think the conventional route, frankly, will get us there to a machine that really is cost effective. I do think that the spherical tokamak has a chance of doing that, and I think the STEP device is actually showing that.
Thanks. I think my short version of that is that the plasmas are much more forgiving. Would that be a fair description in the spherical tokamaks? But the engineering becomes tougher. So, Hendrick, this is all about getting the right magnetic fields. Yeah, go on, start me off.
I wouldn't say the plasma is getting more forgiving. I mean, you can actually sort of, as Steve says, you can actually confine the same plasma pressure or higher pressure at a lower field, and that gives you an advantage. But going into, but essentially the main problems with the plasma that also have the conventional aspect ratio tokamaks have, like disruptions. Yeah, so a sudden ending of the plasma because of an instability, or what we call edge localized modes. So these are relaxation events at the edge because you want to have very steep gradients there to actually sort of have an insulation layer. Those remain the same. Okay, those are still some gaps that we actually have to bridge. On STEP, we have designed essentially these things to handle with that. And then, of course, the whole plasma itself, you enter an entirely new operational regime where your transport that you actually know and love in your current day machines is different. And you have to sort of use digital tools to actually sort of verify your transport assumptions.
I mean, if I could cut to the important part, the big difference, let's say, for most of us outside the business between step and jet is you are going to put a huge amount of heat into the plasma through the fusion reactions. I think 1.7 gigawatts.
Yes,
it's a fusion.
Yeah, 1/5 of that.
So that's nothing like. So that's where life becomes really interesting.
Yes, yeah, and you are entering a regime where essentially the heating from the fusion or the remnant particles from the fusion reaction. So you have neutrons coming out, which essentially give you sort of the deposit heat into the walls and actually breed the tritium in the walls, and that's what's generating your power in the end. But then sort of 1/5 of that fusion energy is essentially dumped into energetic particles. And the step plasma is then will have to essentially confine those particles, and you have to essentially deal with the heat, and you have to deal with the heat then coming out of the plasma in a much smaller device. And this actually drives a certain decisions on, like for example, your magnetic geometry that you want to go with. Yeah, so we studied design families on sort of magnetic geometries, and we came up that you have to go in what we call a double null, where you actually can distribute the heat on 4 diverter legs rather than two diverter legs, and that helps you to deal with that heat.
So there's quite a lot there, but this is all. I mean, the first part of this is. I'll come to you, Morten. The design of the magnetic fields and how you actually operate them to hold the plasma in place.
Yeah, I mean the challenge in controlling the plasma to make it stay where you want and make it do what you want changes quite dramatically when you go from current machines where all the power that heats the plasma is power that you put in, so you can control it, you can wind it up and down. All the current you drive in the plasma, there's a current going around the plasma, that you do also by external means. In step, the main heating source will be the plasma, the fusion reaction itself, which you don't have that direct control over. And also the main current drive effect is a thing called the bootstrap current. It's an internal effect of the plasma that you also don't have a direct knob. So both that current and that power, the majority comes from the internal in the plasma. So the control challenge to make sure the plasma does what you want becomes rather different. You still have knobs that you can control it with, but they are different and they are more indirect. So these are the sort of main differences in control that you encounter in keeping the plasma where you want it, controlling the fusion power.
I mean, I don't know if this is the right question. I don't know what the differences between the fields that you'll be using on step, or you imagine using, I should say, on step, with those that were on jet or those on ITER. I guess it's a smaller machine, but the magnet's more. This is beyond me, so help me.
I mean, the magnet, the control of where the plasma sits in terms of what we call the actuators, so the magnets that we use, is fairly similar. It's the same sort of principle. So in terms of controlling the shape of the plasma, the actual control problem is more on how do we, in order to control the position, you want to know where the plasma actually is. So measuring the parameters of the plasma that you want to control becomes much more difficult in step as well. So a control loop becomes more difficult to implement in step. And this is even for things that are like in a conventional machine, so the magnetic field.
And I don't know, Damian, am I right? The other thing is, because this is not a research machine as such as a demonstration machine, the idea is you don't have all the diagnostics and experimental equipment that you have on something like jet or ITER.
I think indeed, and already on ITER that's the case, that they will have less diagnostics in a lot of ways than existing machines. And it's part of the real goal behind it. It's not going to be there to do physics. It's there to produce electricity or to demonstrate it is. On the other hand, from the start to when you're going to be generating electricity, you need to make the process where you learn how to make that machine operate. So it's not quite at the level, you don't want it to be quite at the level where you're almost flying blind, but you are going to be restricted. And you're also restricted, which we didn't cover, that the diagnostics in a fusion environment, a real fusion operating environment, become more difficult because of the fact you have the neutrons. And this is already something we got some experience on Jet slightly when we went into the DT campaign, the deuterium-tritium campaign. We had to remove a number of the diagnostics because they would not have functioned.
They just get busted.
Yeah. In the first DT experiment, the very first time tritium was used in any machine in the world on Jet, one of the key signs it worked well was that the camera was damaged. So this is one aspect of the control, and this is where the knowledge base that you have for how can you make an operating plasma scenario for your reactor has to be advanced enough that you hope that the amount of work from turning it on to getting it to deliver is as much of a straight line as you can, and improved modeling and improved control algorithms and improved use of real-time control in the operation are two things that many people have identified as key to that.
Steve, can I just go a bit high level with you, which is when demo's working, and if for you the signs of success would be what in terms of the, I don't know, the density or the power of the plasma, the duration? Give me a sense of what sorts of parameters people will be looking for.
I mean, that's an interesting question. I mean, fundamentally, you want to see more energy coming out as electricity than they're going in. That's a very simple parameter. I think what we should say is, the Jet results of last December and the results from Jet generally have shown that we can get the conditions for fusion. So we're not looking at saying, can we get the temperature high enough? You've got to get about 100, 200 million degrees in order to get really into the fusion regime. So we can get the temperature high enough, we can get the densities in the plasma, etc. But we want to be able to do this in a device that's not humongous. We want to do this in a device that's not too expensive. And the spherical tokamak offers that possibility. We haven't yet, in any of the spherical tokamaks in the world, and the leading ones are MAST at Cullum, and we're about at Princeton to finish the upgrade of the National Spherical Tokamak Experiment, NSTX. Those devices are just knocking on the door of fusion conditions, because the spherical tokamak is a Johnny-come-lately. It's it's the more compact design. It's a more streamlined design. I go back to something you said, Rolly, which was, that the spherical tokamak, the engineering is harder. In some sense, it is. The hole down the middle is narrower, but because the plasma may perform a lot better, that makes the engineering easier. Because when the plasma doesn't perform very well, it means you have to make it bigger. Bigger things are always harder to engineer. It just gets harder and harder. And I think that these next few years, as the results from the experiment are combined with the analysis from the STEP group, and we're doing some reactor studies at Princeton too for the spherical tokamak. We have a design called STAR. These interaction between science and engineering and what's actually deliverable, right? This is the dynamic that we've now set up to sort of converge towards that 2040 date.
I mean, one of the big differences between Jet and STEP will be, so the magnets are going to be, well, you better tell me, are they all, who wants to tell me, Morten or Hendrick? They're all superconducting, and are they all?
Except for one.
Yeah.
So there are some non-superconducting. So in this middle hole, we actually sort of designed also a solenoid. The normal tokamak operates like a transformer. So you essentially run current through one coil, and then you induce a current into another coil. Another coil would be the plasma.
Yeah.
Now a reactor sort of real commercial reactor, it's very hard to imagine that you can actually run it like that. And this is also one new thing about STEP. You're designing for the first time a machine which is fully non-inductive, which means doesn't actually use this transformer action.
Sort of self-starting.
No, we started with the STEP itself has a sort of like a very small starter engine, okay, so which starts a little bit of a plasma, sort of a tiny plasma, which has about 2 megaamps of plasma current, and then we have to bring this up to 20 megaamps of current, fully non-inductively with our heating and current drive systems. And that is absolutely new. I mean, tokamaks have demonstrated that you can drive plasmas non-inductively, but essentially sort of the ramping up of it and then sustaining it, and that makes the whole plasma absolutely steady state. So this plasma, in principle, if it sits there and well controlled, okay, sits
I see some
sits there,
Yeah.
and can actually sit there for eternity, yeah. Also, as long as you need to actually sort of then exchange parts of the machine because the walls and things like that get hammered with particles, and they have to be at some point exchanged. Blankets have to at some point be exchanged, but the plasma itself should be actually just living there.
So it's generating its own current, its own magnetic field that then interacts.
You drive. Okay, the plasma, the tokamak always generates a little bit of their own their confined magnetic field by the plasma current you drive into it. Yeah, because you can't confine a plasma simply by a toroidal field. You have to sort of twist that toroidal field. Yeah, and in the tokamak, this is done by the current which is driven in the plasma. Yeah, so and we use essentially the pressure drives the majority of that current because self-driven current in this geometry, but then the rest sort of about 20% of the current, okay, 10-20% of the current we have to drive with our heating and current drive systems, and that makes also the plasma very unique because essentially changing things in the current drive there nowadays you would simply sort of change a little bit of the swing of the current swing in your solenoid, okay, to change your current. You don't have that anymore, and also of course you change the heating suddenly of the plasma, and there's a very non-linear dependence between what your performance of your plasma is and what heating and current drive you actually put into the plasma, and this is what sort of Morten has to deal with.
I mean, we'll come to some questions in a moment, but I'm quite curious how designed in from the start, once you start soldering bits together, will be the physics of the plasma that you have, or obviously I saw all kinds of stuff being done when I came the last night of JET here, and they were doing these inverse triangularity stuff, and so presumably there you can play around with magnetic fields quite a lot.
We can obviously vary, but the room for maneuver is much smaller because the vessel around the shape that the plasma can take is smaller in step. We have this design that is a double null that Hendrick talked about, so we have a diverter, so an exhaust at the bottom, but also at the top.
The double null is, so you go, basically it's a zero sort of line at the top at the bottom.
The null is where there is normally the field lines go round both poloidally, so round in this way and round in that way. But there's a point where the field line goes only round toroidally, and that's called the null. And we have 2 of those. So on JET, we only have 1 of those. We can make 2 or could make 2 on JET, but the machine is not designed for it. On STEP, you have 2 of those. And that spreads the power load to the walls over a bigger area, which means that the power per unit area is smaller, which is quite good because it's a huge power load. So that's one of the reasons. But it restricts how much you can move the plasma around. You could move it around a little bit, but then you will have problems with the power loading.
I mean, it sort of feels to me like you got to get the design right in the first place. Really,
I think for any, I think for any of the machines that are coming up, or if you look at ITER, STEP, and any other proposed design, I think that's true for anything when you move to the bigger the scale, that you're going to have less freedom. I mean, you could already see that when you go from the machines, the Zeta or whatever, the many machines you were talking about earlier, all the way up to JET. The amount of freedom you got. I mean, JET's a special case in many ways because you hacked a diverter into it halfway through, but you lose the freedom as it goes up. You will constrain it. So I think that's true of anything that we're going to do that's a fusion reactor.
Right.
And I think that's something that the STEP team have kind of embraced already and understand, and this is a key driver in, in how we operate, and the parts that Chris talked about, that you have to go through that iteration, and that you will have to innovate. You might have to innovate ways that you can adapt that you don't think you're going to need now.
Steve, you're bursting to come in.
Yeah, sorry. I think one of the things that's happened that really helps us here is that over the 50, 60 years of fusion research, most of that period of time, our understanding of what goes on inside plasmas was sort of semi-empirical. We weren't able to really calculate what goes on in detail. We had some physics understanding, but that didn't translate into actual predictive understanding. In the last 10 to 15 years, that's changed dramatically, because the computer models and the theory has sort of matured to the point at which we're able to calculate in some detail what that configuration actually means in terms of heat loads on the wall and in terms of transport and things like that. Sorry, my iPad keeps recognizing me raising my thumb. But this is a huge step forward, and these models were, came out of theoretical understanding in the 60s and 70s. You think of people like Brian Taylor and Jack Connor and Jim Hasty at Cullen, developing the models of gyrokinetics, and here at Princeton, those models were taken forward into nonlinear regimes. And now you've got people working on the step design like Dan Kennedy, who's an early career researcher working on that, doing calculations of how actually the turbulence will work inside this reactor design. Those calculations are pretty darn good. They have some veracity, which they didn't have 10 or so years ago. So we're able to use the computer in some sense and a digital design philosophy, which you can see in the STEP program, both on the engineering side and on the physics side. This is the new paradigm. This is pretty exciting, and it's come because we did the science.
Right, thanks. And I saw a big chapter on the digital need STEP. Slightly less than I intended. I wanted to let people here have a chance to ask some questions. First of all, though, who's here from STEP? Hands up, please. Don't normally do this. Okay, so I'm told that's the last time you're putting your hand up, unless there's silence. You've had your say internally. Well, I can't actually see anyone because of the very bright lights there, but has anyone else got questions? There are microphones either side. Have you had? I can't see. This really is hopeless. I'm going to get out of camera and maybe be able to see some people. Have we got any questions up there?
Hello, Richard Pearson from Kyoto Fusioneering. I wonder if you could comment on what the STEP team has done in the way of looking at what happens when we reach burning plasma conditions. So, for reference, it's commonly known that when we get past around Q fusion of 3, that something might happen when we have more alpha heating. Can you comment on what STEP has done in relation to this? What's looked in?
Morten.
Shall I take that one? Okay, yeah. I mean, we've done quite a lot of work on simulating, let's say, burn control at the point where we are dominated by alpha heating. And we've done simulations with simplified codes to see, can we actually control the fusion power out of this plant? And that looks very promising. We have a nice poster being presented at the SOF conference, and we've shown that we can, within this fairly simplified modeling, reduce the fusion power quite significantly without breaking all sorts of constraints on density and current profile and things like that. So yes, we are definitely looking into how the burning plasma will behave and how we control it.
Happy? Yeah, more or less.
I mean, I'm sure I can make a much longer answer, but...
Steve, Hendrick, anyone to add on that?
Well, I mean, maybe you can say something about how we plan to actually sort of ramp up into these fusion conditions for STEP. So in the early phase, you want to actually sort of, because you don't have any pressure that drives the current. So you have to drive the current all auxiliary. So you actually try to go to a very sort of the lowest density you can go in the plasma. And we do this up to the point where we actually have achieved the full plasma current. Yeah? And then we actually sort of ramp up the density in order to actually bring the fusion power up. And we looked into this phase, of course, in detail, because there is sort of a little bit of a minimum you have to go through in current, in sort of the current you get. And we've looked at this also with respect to sort of instabilities that could be driven in this. But in the spherical tokamak, it turns out, and in the particular sort of configurations we're running, it turns out that yes, there is, for example, a very strong drive of these instabilities, but the damping is even stronger, and therefore we don't seem to have a lot of those instabilities. But of course, this is still going on sort of at the forefront of research, yeah, to actually sort of bring, because you're actually sort of taking the sum of two large quantities of the, and then you actually sort of need to know that you actually sort of that you do your prediction accurately.
I think this is a good example of the sort of modern fusion program. What Hendrick is talking about is that we've done calculations of that regime. We've never been to that regime, right? No spherical tokamak has got to the point at which the fusion is heating the plasma and sustaining the plasma. But we had the calculations there. And the program at Princeton, the machine that we're building at Princeton is called the National Spherical Tokamak Experiment Upgrade. And it has a lot of what we call neutral beams. And they will introduce very fast moving ions into the plasma, which simulate the alpha particles that are produced in fusion. So you're able to produce kind of the drive and the damping that Hendrick is talking about that works on these instabilities. If those instabilities arise, they throw out the alpha particles, which produce the fusion heating, and we won't get to fusion. So it's very important that we stabilize those instabilities and that we work in a stable regime for them. We think we know that's correct, but on the National Spherical Tokamak, we will do experiments to really confirm that those predictions are correct. This is this interplay between the existing program and the science that we're doing now.
Well, if I could just cut in, this is the last minute and a half, and I don't know whether Steve or one of you wants to answer. JET's closed, ESA's not running, we've got some big experiments going on in China. NSTX, I think, is not running at the moment. Where's the physics of actual DT plasmas going to come from that will help these people beyond computer modeling?
It's a good question.
NSTX.
I mean, all we've got at the moment, what we've got is we've got the results of some of the results from JET, which are a step in that direction, but compared to a spherical regime and a full burning plasma are still a long way to go. We did experiments specifically on how alphas and instabilities would interact, but we were able to do a few pulses with a small amount of time, and it gave tremendous work, and it did tremendous results compared with that modeling. So we're able to look over here at how the model compared with what we had, and then we've got to move on into the next step. Next levels. I'm trying not to say with step every time I do that, but
well, I noticed Chris. I think it was in Chris's paper. He used the word extrapolation an awful lot,
yeah.
Which I think is a good one.
But there are things we won't find out until we have the machines that are big enough to show them. That's part of what we say is the how fusion is and what we accept, and that we embrace the challenge.
Yeah.
You know?
Yeah. I agree that until we actually do step, right, then we won't know everything.
I think what's also important is to understand that one of the big successes of JET was that essentially they predicted quite in large parts how they would perform based on the deuterium experiments. And those deuterium experiments we can actually do in our present-day machines. MAST-U will be actually sort of capable of strong heating from 2026 onwards, and actually we'll test current drive schemes that we actually want for step. Step will have similar heating power to NSTX-U at that time. Yeah. So we can actually look into those plasmas. Now the extrapolation or so the regime is very far away from MAST-U and to step, but we can test parts of the plasma and the important and very important parts of the plasma.
Very reassuring. Brill.
In this machine.
Okay. Thank you very much, Steve. I don't know if you're going to stay and listen to the rest, but thanks for that contribution. Thank you, panel. I'm very mindful that tea and biscuits wait, everybody. So for the next panel, I think we're actually going to talk, this is a really interesting part, I think, of the afternoon. We're going to talk actually about the practicalities of this machine with Joe Mills, is there, Sally Forbes. Okay, you're all in a row there. Sally Forbes is a Fusion Safety Advisor to UKEA. Ezzat Nasar is the Confinement Product Lead, and Chris Lamb, the Remountable Joints. I'm actually going to, I'll start with you, Joe. So the part of the whole idea of this is this will demonstrate you can actually have a commercial reactor, which means it's going to be maintainable. We've often talked in the press about the fantastic work with the robot at JET. You made a nice analogy about keyhole surgery to me when we were talking earlier. Just take us through about how big a step it is to rethink the way that a machine like this should be built.
Yeah, sure. I mean, I suspect everyone in this room is fairly clear on one of the main challenges of getting power from fusion neutrons is those neutrons interact with the materials in the wall and effectively create a sort of radiation environment that means humans can't go in. So we're going to have to use robots. And I think we take it for granted how flexible human beings are, how good they are at fixing stuff and replacing stuff. But even doing something as simple as doing up a bolt, you have to think a lot more carefully when you're using robots, which is what we'll have to use for not all of it, but for large parts of a power plant prototype like STEP. The other challenge is, particularly when you go from a machine like JET to a prototype power plant, is you have, as well as the radiation environment, you have potentially higher temperatures because of the decay heat, you have some potential magnetic fields. And on STEP, one of the trade-offs you make by trying to make this machine compact and small, or smaller and cheaper, I mean, these are still big machines, is how little space you've got to deal with. So to go in and do anything inside this machine is non-trivial. So that drives at least two sort of philosophies, design philosophies. One is, and Chris mentioned it, to design in your maintenance strategy right from the get-go and really make some quite design-driving decisions simply to do with how you're actually going to get in and look after that machine. And there's a number of examples already where they've changed the shape of the machine to do that. And the other one is to keep things as simple as possible. So you don't want to, you will have to do some keyhole surgery, going through some of the ports to do stuff like that, but you really want to keep all the stuff that's inside the machine very simple. Just go in, grab, pull out. You don't want to do all sorts of fancy stuff because the sensors and the actuators just don't work in that environment. So the team has really done a great job of starting with those philosophies in mind and really thinking about that right from the start as they come up with the conceptual design.
I want to go to the magnets because they seem to come up again and again and again. So these are the magnets are going to be the high temperature superconducting magnets. They were just, the first papers on that were just coming out when I started as a science journalist, so I've been waiting for them to have a pretty decent use for 40 years. But you want to be able to remove them, or you need to move them to get access. Talk me through that.
So yeah, I think fusion is the killer application for high temperature superconductors. First discovered in the 80s and has been applied at small scale really until now. And we've had some really promising developments in the States recently with meter scale high temperature superconductor magnets. So that's not in doubt. We need high temperature superconducting magnets. One of the main advantages to enable maintenance is the thermal efficiency and the thermal margin that high temperature superconductors affords you. So essentially, they operate at a sweltering 80 Kelvin, as opposed to a handful of Kelvin for conventional superconductors. And that sort of range means that the magnet is essentially more stable. And what that means is that you can introduce resistive elements to the magnet, which alters its temperature whilst it's operating, and hopefully you can accommodate that and allow the magnet to operate stably. So that's why we're introducing the remountable joints into our high-energy toroidal field coils, because we believe that the HTS is essentially an enabler for that.
So you're just I'm sorry, you're going to have to take me back to my, as it were, university physics. So basically, your windings are going to be mostly superconducting, but you'll have a short length of, as it were, copper, or probably something much more fancy than that. And that will still carry the high currents.
Pass you over to Chris Lamb, who leads on the remountable joints.
Yeah, so typically, as you say, the magnets are wound in a continuous coil to generate the plasma. The greatest stability of HTS, high temperature superconducting magnets, is that there is some margin there that you can introduce small amounts of resistive material, and we're talking small amounts. So what we're proposing to do on STEP is to break or segment the toroidal field magnets that are doing a big job of the toroidal confinement to access the machine. And this comes back to Ian's point up front that we're trying to design a maintainable reactor. So due to the radiation life of the magnet components and that slender central assembly, it's very difficult to shield the magnets for a long lifetime. Additionally, we want to access the vessel to maintain large sectors of the vessel and not have to do the keyhole surgery. So we're introducing remountable magnet joints, which have a small amount of resistive material in those large HTS magnets.
I mean, Joe, can I just come back to you? So the idea is that some of these things can, or all of them can be removed, and is it for replacement, or is this for access to the vacuum vessel?
So yeah, the STEP concept is effectively a hybrid approach where there will be so you're trading off a downtime with ease of access. So by having the remountable joints in the TF magnets effectively form like a cage that traps everything inside. If you can break those in half and demount them, effectively you can take the lid off, and that then gives you much better access to go in and get the big heavy stuff from above, from a crane, pull that out, and take it into an environment where you can maintain it away from the harsh reactor environment. So for the big stuff, where you have to replace a whole diverter exhaust system, for instance, you have no choice but to do that, and you just accept that the machine will be down for a significant period of time, certainly months, if not years. But we also have the sort of jet-like approach where we can go through ports to do some basic inspections, possibly some small repairs, not a huge amount, and we need to be realistic about what can be done, but that means if you have a small issue that needs checking out or fixing, you can hopefully go in, keyhole surgery, sort it out and come out and keep the availability up. Coming back to Chris's point, availability is so important here, so that's why they've gone for this dual approach.
I mean, the mechanical reliability and stability of this machine, I think, is going to be a very interesting one. Also, you're going to have a completely different radiation environment, which is why I want to ask you, Sally. As I understand it, another experiment, as it were, essentially, is to find a new way of regulating a facility that's not a fission facility, but isn't just a chemical factory or something. So your involvement is to try and work out how this kind of operation should be regulated.
Indeed, innovation doesn't just apply to the science and the physics, it's all the management processes around it. So we've heard, if I talk about hazards, we've heard about the fact that you have radioactive tritium as a fuel, we've talked about high temperatures, we've talked about high magnetic fields and cryogenics. So really, when you're having a regulatory framework, you have to have something that is proportionate to those hazards. So several years ago, the government started looking at this and held a consultation on the way that fusion should be regulated. And we kind of supported that, looking at what some of the accident scenarios might be, your kind of worst case accident scenarios, to kind of understand where it's at in that scale of things. And it was determined through that the hazard profile and how it could impact people was more like those kind of larger chemical, industrial or hospital irradiated type facilities, and not on the same magnitude of nuclear power plant, for example. So taking into account that proportionality, the fact that you would be working in an innovative environment and you had to kind of enable all these decisions to be made through time, the decision was made to stay with the same regulators that we have for our current facilities here at Culham. So that will be the Environment Agency and the Health and Safety Executive. So neither STEP nor any other fusion plants in the UK will need to have a nuclear site licence. They won't fall under that regime. So it has been really important to kind of understand the background to that. My particular role of mine and my team is to kind of work with the government and the regulators to kind of provide that access to the science and the learning so that people can kind of upskill to regulate that in the future.
I mean, the other one, it will be the activated materials. Presumably there's going to be a lot of activated steel and...
Yes, there will be that, which will obviously have some radiation fields in operations, hence you have your huge concrete bioshields. That will also result in some, obviously a significant amount of radioactive waste as well. So part of the innovation doesn't just stick with the machine itself, it's how you deal with those materials, either when you're replacing it through life or when you're decommissioning at the end of life. So a lot of research, and again some of the papers covered this, on how you can design and build materials that will reduce that amount of radioactive waste in the end, how you can detritiate that to reduce the level of radiation, but also to recapture the tritium to use it as a resource. So the management of waste, both in design and your choice of materials, and then how you can manage that to reduce the amount of waste, reduce the amount of radioactivity, maybe reuse it in future plants is a big consideration through life as well.
I mean, briefly, what bigger difference do you think a new approach will have in terms of making, in Ian's terms, the whole concept financially viable in the long run?
Yeah, so and any safety assessment is a risk assessment, whether it's for a laboratory or a nuclear power plant. What it means is that we can look at comparable industries. So a lot of the hazards are found individually in different manufacturing industries or accelerators or things like that, is to use the expertise that the regulators already have in those areas, but kind of bring them together. So we'll use existing regulations and frameworks, but that innovation will be to understand all those kind of cross-discipline interactions, and also to kind of understand, how if a particular accident scenario is not really going to impact people, then you don't need to put a lot of safety systems or have a lot of control around that. So it means that we won't be forced down a route of kind of over-engineering anything, because it can't have the same impact, for example, as a large nuclear power plant. So it should make sure that the safety engineering is proportionate and not too onerous without giving us any extra safety and environment benefits.
When I was at ESA, I got the impression that being regulated as a nuclear plant was actually a bit of an unnecessary problem and an expensive problem there. What about I'm quite curious about the materials and engineering challenges here. So maybe we should go back to the high temperature superconducting cables. Now, I think I heard that they are being used is it at Princeton on NSTX, or is it in Commonwealth Fusion?
So Commonwealth Fusion Systems are sort of pioneering the HTS technology, and they'll be using it in Spark and ARC. Plus, we've got our friends down the road at Tokamak Energy who are developing HTS technology for for tokamaks and other applications as well.
I mean, so I suppose what do you need to learn between now and then? This is coming back to this question. What do you need to know about these materials between now and 2040, when have you start building, in terms of their mechanical robustness, their resilience to, I don't know if they will be exposed at all to neutron fluxes and all those kinds of things?
So that's an active area of research. It really constrains the mechanical design of the device, because HTS is essentially a Rebco layer which is deposited on a tape structure, and that layer is very brittle. The layers are also liable to delaminate, so the failure modes are quite constraining. And what that means is that you need very robust mechanical structures around those magnets to withstand the huge electromagnetic forces that are generated. There's a lot of talk about compactness. That is even harder, you know, to sort of fit in all these structures to be able to contain these magnets. But in addition, so that's the sort of design. We've got huge challenges down the center of the machine, that was also mentioned, very, very constrained for space, and massive temperature gradients. So we're looking at 100 million degrees in the plasma, a few hundred degrees in the first wall, and then we go down to cryogenic temperatures, and things are trying to expand, other things are trying to contract, and there's little gaps in between them. So it's a very difficult problem in a spherical tokamak, given the slender nature of the center rod. But going back to the tape itself, we're doing that. Still a lot of research is needed to understand the performance of the tape at high fields. So it's a huge advantage to be able to have this sort of magic material which can really pack a punch in terms of current densities to fit inside our center rod at high field. But there's a lot of uncertainty around how well this tape performs. So there's been some great advancements in terms of the number of suppliers of tape and the volumes ramping up around the world, but there's still a lot of variation in performance and very, very little tests at 20 Tesla, say, of a range of tapes. In addition to that, there's radiation uncertainty as well. So we were talking about waste and regulation. How this tape performs in a challenging environment, like in the middle of STEP, is also uncertain, and then obviously the limit. So how much dose...
So on the inside, they'll be getting a pretty substantial dose,
and down the center in particular, where there's very little space for shielding. And you've got this, you know, all the inner limbs of the toroidal field coils going down this middle center rod. You've got all that tape being bombarded by radiation, and there is uncertainty around how long essentially that tape will last. So yeah, the active area of research. We are actively bombarding
is it being
to learn
done
more.
here, or I mean, are there test facilities here, or what?
Yeah, so we've got test facilities in Birmingham University. We're collaborating with Oxford University. So yeah, in the UK, but also globally. Yeah.
And also the interconnects. Presumably, they a separate challenge.
Yeah, separate and connected, literally challenge, but. And there's a number of challenges, some of them shared in terms of managing those huge electromagnetic loads. If you then split your magnet, where do you think it wants to break? So actually designing remountable magnet joints that can also have a structural connection that bypass those loads is a big challenge. Resistance, we mentioned the stability and being able to have a small amount of resistant material. But we really want to limit the heat generated, because that has to be cooled at a very low temperature where the penalties are huge, and we don't want to erode our fusion power. So we're really driving hard at low resistance, and the other challenge is the remote maintenance challenge. So we're working out how we sort of align these magnet joints to a really high accuracy remotely, no human intervention. So these are all sort of big challenges, and space is the other one in the spherical tokamak. So integrating the full functionality of a remountable magnet joint that clamps shut in that sort of space-constrained environment is really, really difficult.
Joe, I don't know if the other material concerns I saw were, as I understand it, you'd like the inner wall of the tokamak to have as high a temperature as possible. But I mean, I don't know if is that one of the areas of research at the moment, or what are the other sort of material research concerns?
Yeah, I mean, materials, as you'd imagine, is a huge topic, and we have a dedicated materials division within UK AEA that's doing some fantastic work in these and other areas. So yeah, I mean, obviously, the law of thermodynamics suggests the higher temperatures you can get in terms of your first wall and the coolant is that the more efficient the system becomes, the more electricity you can pull. But then material properties change as with temperature and with radiation. So again, there's an awful lot of modelling going into seeing where's the sweet spot in terms of what operating temperature we should operate at, what coolant we should use. And again, it's all these. This is kind of gets to the heart of the integration challenge. You can do a bit of research over here and say that this temperature does, this material does this at this temperature and fluence, but it's only when you start designing a machine like STEP where you start to have to grapple with everything all at the same time and make these trade-offs. And I think what's been so impressive over the last few years is how they've made some quite difficult decisions to try and pick the best option from an infinite number of combinations.
Yes, and I got the impression from the Royal Society document that there have been a huge number of choices. Well, Chris talked about this, that you've been narrowing down along the way. I'm hoping there are some engineers and material scientists in here who might have better questions than me. We've got about 10 minutes for some more questions here. Again, I cannot see anybody. In the front, one in the front row here. Oh, and someone back there as well. Since you're going to get there first, let's hear from the back.
It's Valerie Jimison here, Development Manager for the Fusion Cluster. How open are you to learning from innovation that's happening in the private sector, from the likes of Tokamak Energy and their high temperature superconducting magnets, or from some of the private fusion companies working on new materials?
Very open. I mean, what we're trying to work on for the next 4 to 5 years of the program is building up a strategy to partner with industry. We need to strengthen collaborations, increase collaborations with academic institutions, research institutions, but industry, Tokamak Energy in particular, and others will be essential. I mean, one of the biggest challenges that I overheard in a conference recently was one of the biggest challenges to fusion was that we're designing superconducting machines with non-superconducting engineers, me included, and there's a capability problem. So we really need to build capability by working with the private sector and growing together. It's a key part of the strategy going forward.
Another one back there.
Isabel Horton from Atkins Realis. Building on Valerie's question, and coming back to the theme that we're talking about maintenance and availability, what do you see are the options for learning from other industries for creative and innovative solutions to some of the maintenance challenges?
I'll just take that. I mean, I'm going to echo everything Ez has really said, but in a different field. And one of the reasons we've adopted the vertical maintenance strategy is that it leverages more capability from nuclear fission, oil and gas, and equally the partnering strategy over the next 4 to 5 years is designed to enable partnerships that are going to help us pull in the not just innovation but best practice. We don't want to reinvent the wheel as well. So I think there's a lot of good practice that we can leverage and access a wider network of collaborators to solve some of our problems. So very much akin to the magnet strategy approach, really.
Have you got a microphone? Yeah. Just speak.
There we go. Aslan, actor and technology scientist. Thank you so much for today's lovely event. My question would be, across the plot, we've got Helion Technologies, and they've bought their first purchase agreement with Microsoft. So they're going to have a first plant that's online by 2028 to reach the target of 2030 carbon neutrality. I was wondering whether STEP, in their computational analysis, start to look at small language models, quantum APIs integrated with biological neural networks to be able to harness all the data that we've got. And by the way, small, not large, because large language models obviously got all the rubbish from Reddit. With a small language model, we can put all the physics and it's actually correct. Yeah, any...
Computing, yeah.
So, I mean, short answer, yes. I think to take this next step, even though, you know, the machines like JET are an incredible machine, to go from JET to a prototype power plant is such a leap. We don't have the time or the money to do the traditional test, build and test for everything. I think it's been mentioned a few times by other speakers, but, you know, modeling has come on massively, and now with sort of exascale computing, we're already starting to understand how we can run our codes at the exascale on machines like Frontier in the US, combined with AI and machine learning to speed up the optimization and build surrogate models and these large language models. We absolutely are looking at how we're going to harness that to keep us on track or even accelerate. So that's a big part of the program. A significant fraction of the STEP budget is going to go into modeling and digital and how we can use AI. So absolutely, that's going to be hard to be. Like most industries, we've got to be honest and say this is early days. So exactly how that's going to work and how much of a difference it will make, we can't sit here and say it'll solve everything overnight. I'm sure it won't. But we have a small but growing, incredibly capable team who's figuring out how to do that. And what we need is to democratize that knowledge into the supply chain. So we've got lots of companies who are working with us to develop these models. To go forward.
I mean, if I can just expand this, it's. I think this session in particular highlights the need for industrial collaboration outside the Atomic Energy Agency and so on. How? I guess you know a lot of the people already, but how big a deal can this be for UK industry in terms of building up supply chains in high temperature superconductors and other materials?
It's enormous. I mean, I think someone's described it as a moonshot. It really is that. It's so exciting that the UK has actually decided we're going to go for this. And let's be clear, a national lab is not going to build a machine of this scale. This is a mega project. I mean, you know, we don't know exactly what size it is, but if you just picture Hinkley Point as an example of the sort of scale and complexity, and that's going to require a supply chain of thousands, if not tens of thousands of people. So industry is going to build this machine, and it's industry that's going to design and build the commercial reactors that follow. So building up that supply chain that doesn't really exist yet is an absolutely key part of STEP, and also demonstrating economic benefits as we go in terms of spin-outs and technologies for the country is as important as getting to the final goal. So yeah, industry supply chain is absolutely essential.
Yeah.
A small magnets example to that. So we mentioned Commonwealth Fusion before and the advances they've made with their high temperature superconducting magnets. And I think as an outsider, you sort of look in and you think it's all going on in MIT, when in fact, if you read the papers that were published recently, there's hundreds of suppliers that are acknowledged in each one of those papers. So they're, like us, building that network to be able to realize these technologies. It's not all done by ourselves.
Well, and I mean, it's presumably also incredibly important that at the end of this project, assuming it's successful, you have the manufacturing capacity and capability within the country that can then start building the commercial machines that will follow.
Absolutely, and I think what we've got to bear in mind is if we can build this. If we can build this supply chain and create companies that have got IP and abilities to build the subsystems that go into a fusion reactor, a lot of those are going to be somewhat concept agnostic. So, you know, we've picked a concept. This is our best bet, but we'll see how it goes over the next 15 years. And if we build up the supply chain and the community, the world decides actually it's going to look a little bit more like this, hopefully all that that supply chain can still be incredibly valuable to the UK in terms of building those slightly different reactors of the future.
And could also, just one other thing is, we were talking about the safety thing. Is this an experiment for you? I mean, are you going to design what you think are the right regulations and hand them over, or are you going to be sort of watching the scientists and engineers work and thinking, actually, no, we need to change this, having a conversation?
So, in essence, we'll be using existing regulations, ionising radiation regulations, for example, or things related to other industrial ones. So, it will be a case of, as I know, sort of mixing and matching those, but the regulatory bodies themselves will be learning along with us. So they come for familiarisation visits to here and will kind of learn about the specialist topics that we have in fusion. So in a way, there'll be a little bit of kind of working in parallel. So with industry, not just STEP, but other industry, because obviously there are different technologies out there as well. So the regulatory framework will be technology agnostic as well. There's also learning around the world. So we have been world leading in saying we will have a sort of framework that will be specific to fusion. So working with other countries that are also building up their knowledge in fusion or have regulated existing ones. So I think there'll be a very good relationship there. Obviously the regulators are there to regulate, but they will have to learn and innovate alongside the technology innovations as well.
And if there's time for a very quick question, if someone's got one, or it's time for tea. I'll reconvene, I'm not quite sure how soon, we'll reconvene in 20 minutes back here, and there's some really interesting tech stuff we're going to go into next. So thank you very much so far. Thank you very much to the panel. Well, actually, I'm not even going to take this order, but you are first. Okay. Yep, we're ready to go. So this third section is, I think, coming to some other really interesting engineering aspects, certainly ones I find very interesting about the way that STEP will work. Do you want me to move this or something? It's sounding very tinny. So I want to come to you, first of all, Howard. I'm presuming you've all got the bill in front of you, so you know who I'm talking to. Howard, first of all, so you were the first begetter of STEP, is that right?
Maybe.
Maybe. Okay. If you don't want to take responsibility. The really important part of STEP, beyond anything else, is that it's going to demonstrate you can produce electricity. I was looking at the papers, and I have to say I was actually very impressed and pleased to see big numbers for the power generated in the fusion reactor and coming out in terms of electricity. Just talk me through a bit of that.
Yeah. So electricity or power generation is the main requirement, the main thing that STEP will be judged by. But as Ian said, it's not enough just to produce the power. You have to show that power is commercially viable. So the target for STEP and other fusion pilot plant designs around the world is typically around the 100 megawatt level, which is about, as you say, it's a significant number. It's about 10% of a typical power station. You might not think that's big, but it's about 30 offshore wind turbines, so it's significant.
And it's sustained.
And it's sustained. Yeah. Well, the aim is to make it sustained. So I was going to come to that sustainment thing. That becomes part of your commercially viable thing, because you want to be able to have it operating for a significant fraction of the time, and also it needs to be at a significant level, and it needs to be at a significant cost. So 100 megawatts of power coming out is a key requirement, but then there's a bunch of other requirements that come beyond that. STEP itself does not have to produce the electricity in a commercially relevant way. But what STEP does have to do is demonstrate the pathway, show the pathway for that commercial realisation of power. There are a number of ways to do this, and one way would be to have a phased approach, where your first phase, you heard in the first panel, for example, there's some significant plasma physics challenges. So the first phase should just be, can we produce 100 megawatts of electrical power, net electrical power, which, as Hendrick said, means producing about 1.7 gigawatts of fusion power in the present design of STEP. So that's the first phase, would just be to do that. But then you need to do a lot more. That you could imagine doing with tritium that you would buy. Could you go then you need to go to a next phase where you need to be able to operate in a sustained way, as you said. That means you need to be able to breed the tritium, manufacture the tritium at the same rate as you're burning it, ideally more than you're burning it, so you can keep future power plants going as well. So a next phase might be associated with that. So you capture the neutrons and not just generate the heat and the electricity, but also generate the tritium to then feed back into the plasma. That's also a challenge, because your deuterium and tritium are in your plasma and you're confined by your magnetic fields, but then they diffuse out. And as they come out, they're exhausted, they're circulated round and fed back in again. A typical tritium will do that, round that circle, up to 100 times before it finally has a fusion reaction. So the other thing you have to do is not only breed the tritium, but manage that exhausted tritium and going back in again. So that's what you might demonstrate in the second phase of STEP, for example, the so-called closed fuel cycle. Then there's the maintenance issue. If your reactor is down, it is not producing electricity, it's not commercially attractive. So you want to minimise the downtime of your power plant. That means you need to have a good understanding of the reliability of the different components, and that means one can try and predict that in advance, but really you won't get a handle on that until one operates STEP, and operates it for numbers of cycles of those particular components. So you would now start operating STEP for a really long time, understand the lifetimes, the vulnerabilities of the components, understand the kind of systems that need to go in to maintain those components, either get them out and replace them, repair them in situ, inspect them for the regulatory requirements, particularly if it has safety implications, and that might be a third phase of STEP or a fusion pilot plant, for example, bringing those long phases and understanding the maintainability.
I'm going to come back to you on that in a moment, but the idea is that all of those phases are at least designed in from the start, so that you will have cooling systems for the torus itself. Then you've got the tritium breeding part on the outside. I believe that's where most of the heat will be. Is that right?
Yes, so one can imagine protecting certain components from the neutrons to a certain. If you have vulnerable components, you can think about putting shielding in there to protect them. The blankets, their role is to catch those neutrons and generate tritium. So by definition, they're going to get blasted with 14 MeV neutrons all the time. The thing is
and they're capturing the heat, the energy from those neutrons, and some of those neutrons are going to collide with lithium ions. And they're going to produce, okay, I guess they'd have to, yeah, but they'll have deposited heat on the way.
Yes, well, in doing that collision, they'll give up their heat. You'll have a coolant going through the blanket. That coolant will extract the heat, which is, then you can either use that directly for your for industrial heat as a, you know, that's a big product, or steam turbines generate electricity. Absolutely.
So, who wants to talk about tritium? Because this bit, as far as I can see, this is the bit where the principle is easy, the practice is not.
Yes, exactly. And I think the thing we have to remember is that what we're trying to do here is actually breed tritium online as we're operational, extract that tritium, process it, and put the tritium back into the fusion reaction. And this is literally the first time we will have ever done it. And so what we're embarking on here is taking that theory and turning it into a reality. So it's lovely to think of, you've got this lovely fusion reaction happening in the middle, you've got your first wall, you then just put a blanket of lithium around it.
Blanket is such a wrong word,
It's just a blanket of lithium around it that then magically is producing its tritium. Yes, it will produce the tritium as the neutron hits that lithium, and you extract that tritium and put it back in. What does the reality of a blanket look like, this blanket idea? Well, it's about 1 meter thick. Just to help us along the way with that. Is my microphone okay? Yes. Yeah, okay, good. About 1 meter thick. And then what form is this lithium in? Is it in a solid form, perhaps? Is it in a liquid form? And how you decide that leads you to all sorts of interesting engineering challenges. So, if it's in a solid form, it could be pebbles. You've got to contain those pebbles inside something. Suddenly, this isn't a blanket that we're talking about. This is more like a radiator filled with some kind of lithium. It might be a radiator that is filled with liquid lithium. It might be a radiator that is filled with a solid form of lithium. And you've got to both extract the heat, cool down that lithium as it's forming that tritium, because that's an exothermic reaction, and take that heat out and then take the tritium out, which Mike can talk about a little more. But the materials that you're dealing with in here, you've got neutrons coming in, you've got an exothermic hot reaction going on. You've got to have materials that can cope with all of that. You've got to have lots of channels, because you've got to get that surface area so that you can get your tritium being bred and you can extract the heat. You're suddenly talking about something that looks actually quite complicated, no matter what you do, and much less of this simple blanket idea that we imagine.
And if I'm correct, the point is, these are numbers I managed to work out from the various papers. So the inside, the first wall, is going to go up to about 200 200 centigrade. Is that right?
Well, that's good. You'll sit at about 1500 degrees.
Oh, 1500.
Okay.
Yeah,
at the very front face, and then
but
you
the
have
coming out is.
And the coolant will be at around about 400-ish degrees.
But am I right that the hottest water is going to come from inside the lithium?
Yeah, that's right. It's because although you've got the most neutrons and you've got a very hard heat transfer problem on your first wall, you extract relatively cold fluid or gas from that. You then take the neutrons through, you've still got that heat to remove, but you've got an exothermic reaction as you turn your lithium into tritium, and so you get more heat. This is actually great from a power generation point of view. Hotter, you're going to get a higher efficiency power generation system, and it's more useful for industrial plants, but much more difficult for the materials. A lot of materials work in a way that we can understand and we feel fairly secure about up to, say, 500 degrees. You go above that, and you start having some problems with those materials.
But having boosted the energy, so you get another, I think it's 100 or 200 megawatts of power. So that's actually, as you say, very nice in principle. Yeah. So then that's all going to get plugged into the turbines which are outside, and that's getting that temperature as high as possible is one of the things you really want to do.
Yeah, that's right. And it's funny because we are, right at the core of the plant is this tokamak, this highly advanced, novel technology, and then we're going to take that heat and we're going to put it through some turbines. But the challenge and where all the innovation comes in really is not that we're not just producing power, but as people have talked about, we're producing net power. And so we need to do it in a way that's highly efficient. And so, yeah, one of those ways is pushing up the coolant temperature as high as we can, and obviously as the team designing the power infrastructure would like to push higher, but then there's compromises across the plant that you have to work with.
We're talking substantially hotter than Hinkley C, for example.
I don't know that number exactly.
I think they're 400.
But we are talking high, and 600 might not sound extremely challenging in some contexts. Obviously, there are lots of industrial processes that use that sort of temperature, but when we're talking about materials that are operating in a fusion environment with the neutron irradiation, then that becomes more of a challenge.
So how do you get the heat? What I'm not quite clear, you've got your lithium, you want your steam, where does the water come into this? Where does the lithium stop being part of the story?
So the first thing to say is that in that lithium blanket where a lot of that energy comes from, we're actually using helium. And that's because of the obvious safety risks of pumping water through a pipe in a lithium blanket. But what we will do essentially is have coolant pipes running through all of the components. A lot of the heat's coming from the blanket, but also some of the heat's being deposited in other components, and we'll be running coolant through those at different temperatures. And then that will essentially go through a large heat exchanger, and on the other side of that heat exchanger is the power cycle, which will turn that into electricity.
And on site, how much electricity do you get out of your 1.7, 1.9, or whatever it is, gigawatts?
Yeah, so we're producing around 925 megawatts at that sort of current design point. The challenge for fusion is that there's lots of parasitic loads that then need to come off that.
You've got to power the machine.
Yeah, you've got to power the machine. The largest load is the heating and current drive, which you heard about earlier in the panel with plasma. That's on the order of a few hundred megawatts potentially. Then you start getting the loads from the pumping of the coolant, because actually pumping the coolant around itself takes quite a lot of loads as well, particularly having had to choose the helium as the gas coolant in the first wall and the blanket because of the safety concerns, so we can't use water. And then in sort of declining order, you get the cryo plant for the magnets themselves, and then some other parts of the plant as well.
So the plan is out of that 900 or so, you get 100. I think you can get more than that if the wind's, you've got a favourable wind with you. Howard?
Well, 100 is the target.
Yeah.
But as you say, there are uncertainties, so those uncertainties are built into design. Hopefully it will be more than 100. Yeah.
At what point would you crack out the champagne?
One. I've been in this game a while. No, I think you want tens of megawatts because you want something that's commercially relevant. I think so. Up towards 100 megawatts would be a good.
And you'll be at West Burton. in Nottinghamshire, and the idea is that there's already a power connection there, so you
Solving
would actually start powering Nottingham or to a smaller.
So I think though, certainly in the early days there'll be challenges in terms of that continued power.
Yeah.
And we heard earlier about the turbines, but turbines are designed typically to operate. You switch them on, they operate at a certain temperature, and so they're not compatible with a tokamak starting up, operating for a few hours, switching off, starting up, typically. And so there is some development to go there to understand that if one wants to connect those turbines up. So I think the early days, it would just be a demonstration that we can choose the power, like I said earlier, and one would move progressively towards putting the power onto the grid. I would assume, but I'm not an expert.
Yeah, so you're absolutely right. If you think about traditional steam Rankine turbines, we're talking about hours to start them up, and if we're talking about operating initially in pulses to see how the machine works and because of certain limitations and to experiment, then ideally we don't want a situation where every time we turn it off we have to wait for hours to ramp the turbines down and then wait for hours to ramp them up. And you also need, the fusion power can come on and off relatively quickly, but to ramp up your turbines you need a heat source obviously, so the longer that takes, the more you need some stored up somewhere to do that. That's why we are exploring at the moment, instead of a steam Rankine cycle, which is our sort of fallback option, we are exploring a supercompressed CO2, a sort of a variant of a Brayton cycle with supercompressed CO2.
The advantage of what being?
The advantage being that it can start up more on the order of tens of minutes, so half an hour, that's that sort of time, rather than hours.
And that's because you're not having to boil water effectively. Is that too simple?
It's more to do with the rate at which the turbines themselves can speed up. And CO2 turbines, another advantage actually is that they are a lot more compact as well. So while there's a bit more of a development challenge there, potentially it leads to a longer term solution with a cheaper power cycle.
Okay. I've got to look into that.
It's also because industrial turbines pass steam over. And so you don't want so because industrial turbines pass steam over the turbine face, that you have to be careful in terms of thermal loads across the very large discs. So you might think, well, why is it that a jet engine can start up very quickly? Because that's because it's with dry air rather than with steam.
Right.
Yeah. Okay. So
I went to Siemens at
right,
Newcastle some years ago and had a very interesting time learning about turbines there.
Yeah. So if you could dry the air, you could do it with or you could make the industrial turbine unit smaller, or you change your fluid medium for that's going down the main profile of the disc. It is worth though. Can I just talk a little bit about coolant selections? Because you were talking about water and lithium, but I think it pertains to a larger point about if you're when you're sort of selecting your breeder medium, like, whether it's a lithium or a lithium compound, so you're talking about either whether it's liquid lithium or whether it's a solid breeder pebble bed, that you've also got the choices you make there also impact the choices of the coolant you select. So if, we talked about why not water, well, because obviously you can't have that next to lithium, so it forms you to have helium. But then it's not just about the coolant selection, it's also about the material selections. You're in a very hot environment, so all these kind of discussions of what kind of heat you're exposing your blanket to and operating your blanket at are all pertaining to those kind of things in terms of material selections, coatings you might use, coolants you're going to use, breeder blanket. So this kind of the blanket actually offers this interface between the massive heat source that your plasma is providing you and the turbine, right? But it's also got to do tritium as well. So it's doing it's taking something that's extremely hot and then producing it into taking this heat into in the form of neutrons coming out into useful energy for a turbine, but it's also got to do this miracle of producing tritium.
Well, this is the stuff I have to say. This is what I really liked reading in the papers, is that for all this time we've been talking about we need fusion for power generation and we need the tritium and blah blah blah. But it seems I'm seeing really concrete ideas about how you do combine all this stuff together. It's one thing to make the tritium inside the blanket, what you need to talk me through is what kind of process gets it out. I'd also quite like some numbers. I think we had a bit of a discussion. You'll be using, is it about 100 kilos of tritium a year? And you need to make, I think we worked out, it was something like 30 grams a day or something.
Do you want to do it? Yeah. I got the numbers, but go for it.
So I do we get the tritium out first, sort of thing. Yeah, but let's do the tritium out of the blanket first, because that massively depends on your blanket medium. So again, like I was saying before, like the blanket medium you choose, it's then what coolant you choose, it's then what materials you choose. It's also what tritium extraction technology you use. So if the paper talks, focused on liquid lithium, if you're in that sort of sphere, you've got one of the big problems with one of the big advantages of liquid lithium, you get a very high tritium breeding ratio, so you get a lot of performance in terms of the blanket, in terms of producing tritium. But then one of the big problems is that it doesn't want to liberate that tritium. One advantage to that, though, is it doesn't want to liberate it into the coolant. But it also means that it's very difficult to then extract it out of the breeder. So I mean, you're not going to unbolt the side and take the
exactly,
out, yeah. But because it's liquid, you can flow it out into a nearby system, and then when it's in that system, you can mix it with another lithium compound, a molten salt compound. When it's in that form, the tritium then prefers to go into the molten salt. And then once it's there, you can put an electric charge. You can basically use electrolysis, which then bubbles the tritium in the medium. You then push a carrier gas across that, and that pulls the tritium out. Then you use a centrifuge to pull back out your lithium from your molten salt. So that's one option. That's called liquid lithium extraction. You can also cold trap, so you can pull your temperature down of your liquid lithium, and then and once you've doped it with hydrogen, so you put in more protium, and then you've basically got a hydride, so you form crystals as you drop the temperature down. You need to dope it such that you actually get a meaningful amount of the crystals out. You then centrifuge the crystals out.
It's pretty serious chemistry and
it's serious chemistry, yeah. So these are some of the options. And then if you change the blanket medium format, then you've got all different options. And that's like just stage one. You've got to go into stage two then of taking the tritium that you've got out, which is now probably mixed with helium and probably mixed with a doping medium, which is going to be as a hydrogen. You've got to then in that, you've got to kind of then do a load of standard process, well, I say standard, processing engineering to then get that to a format, which is then you can have some fun with, and that means freezing it, cutting it into blocks, and then firing it with a centrifuge into the reactor down a fueling line. So it's a big zoo the fuel cycle was a big zoo of multiple different process engineering stages, all of which have different levels of technical maturity and scale-up challenges.
But this is essentially going to be somewhere between a batch process and a continuous process, which ends up with pellets. Yeah. Now, so the mass of the pellets is what?
Right, yeah, okay. So then that's the other question, isn't it? With how many pellets? So you need to put in pellets at about 5 hertz. And as pertaining to the point that Howard was talking about earlier, which was that your fueling efficiency, that those tritium atoms are going to go around, only 1% of them that fire in are probably going to actually, or gassed in, are actually going to be in the reaction. So as a result of that, you are talking hundreds of kilograms casting round in but the actual the amount that's burning is then a lot lower. So, you've got this sort of strange situation whereby it only takes grams to produce large quantities of energy, but you're going to be passing through kilogram rates. Okay.
Yeah, so it's going to be a lot of, I get that. There's going to be a lot of unburnt tritium circulating all the time, but to keep the concentration up, you're putting in, you said pellets or every 5 times a second?
5 to 5 hertz, yeah.
Okay, and they are deuterium, tritium?
They're about the size of a BB pellet. Yeah.
Right,
yeah.
And they're deuterium, tritium.
Yeah.
And the tritium for that has come from the blanket that you've then processed. I mean, it's a big step. Well, it's a huge step. It's really interesting for me. Is what is what's the state of the experimental science now, and what do you need between now and let's say 2035?
Yeah, there's a huge amount of experiments. I mean, there's a lot being built. There's a lot of interest. We've got a lot of private fusion companies that are starting to build tritium loops and starting to be able to do experiments. There's the Liberty experiment that's being built at Cullum at UKAEA, and all this is to start building this capability so that as we're investigating all these different types of breeders and the coolants that go with them and the structure they're in, so we can start investigating all the things we need to know. Things like, if you've got a solid breeder, how much does it disintegrate as the neutrons hit it? Will that become so much of a powder that you can't get the cooling flow or the purge gas through it to go off to the tritium extraction system? So there is a huge amount of both basic, just material science that needs to be done, of which some loops already exist, and then there is a huge amount as we scale that up that needs to be built, but is being built by a lot of different companies and organisations around the world.
I mean, that's also, sorry Howard, go on.
Steve Cowley spoke earlier about the importance of doing the modelling for the plasma physics, because the plasma physics in STEP is going to be in a very different regime to where we can do experiments. And the same is going to be true of a lot of the technology. So yes, we need these test rigs. We absolutely need these test rigs to give us data, but largely that data will not be precisely the conditions of STEP. So again, we will need to extrapolate. So again, we will need to build up reliable, predictable models to be able to understand how these technologies apply in STEP.
And then you use the experiments to help verify those models, and so you get into the digital world.
Because I was also wondering about the chemistry, the interface between the whatever form your lithium is and the structural materials. At these temperatures.
Oh gosh, that is one of your palette of materials so dramatically reduces once you've got your neutron bombardment, you've got very high temperatures, you've got incompatible fluids. So actually the number of combinations that you can believe can work become very small, and that is the game we have been playing over the last 5 years,
like looking
at all those different ways of doing it, finding which ones we believe could work and what we would need to do to development, and which ones, frankly, can't get us the tritium production we need in the area we've got, or have other major issues with them.
And are you having fights with the people trying to get the heat out for
constantly,
space?
Yeah.
That's why Jenny's sitting between.
What have you started? I mean, to me, the whole point is to get energy out, and it's really exciting to see all this stuff coming together.
I think you mentioned there a kind of a tension between different technologies. I think the first wall to me is a really interesting one. So the first wall is the bit that faces the plasma. It gets absolutely everything blasted through it. So what you need to do is to have something that's resilient to that harsh environment, but you can't make it too thick because your neutrons have to get through it to get to the lithium, and you have to have all these cooling channels right up against this first wall, so your first wall doesn't get too hot and melt or damage, etc. So you've got this really complex layer, which will be a multi-material layer going from something like tungsten maybe right up against the plasma that's got to switch to something that will be highly conducting to get the heat out of that tungsten to your coolant, transfer that to the coolant. What do you do about these cooling channels? How do you maximise the heat getting from that material surface into the coolant and conduct it away, and then still let your neutrons get through to your lithium to breed the tritium? It's great. It's so exciting.
I find this, in a way, the most exciting part. I don't want to be offensive to other people. Well, it's like using the high-temperature superconductors. It seems to me that these are not gambles, but really pushing the envelope. And I find the fact that you're doing that, I find really thrilling. We have time for some questions, not as much time as I meant to leave. Someone hand went up very quickly in the middle. Just managed to make that out. Oh, and there's one down here. Yeah.
Hi there, Peter Walker from Arabelle Solutions, and by the way, I led the engineering team that designed the Hinkley Point turbines.
So was I wrong or right? Or close?
You were a bit wrong. I'm very interested to understand what target you're looking at for your cost of electricity, cost per megawatt hour. Obviously, that's, in the end, all that matters. And I am interested in the size. So 100 megawatts electric, you need 18 of your machines to do one Hinkley Point machine. Every time I talk to these days to the people trying to develop SMR reactors. Their reactors get 10% bigger every time I talk to them because they keep struggling with the fact that they just are not cost effective compared with the large machines. And so I'm just interested to know, do you really think, and how can you get cost effective per megawatt hour? The technologies are all wonderful and exciting, but will it evaluate?
So I'd like to address the 100 megawatts from 1.7 gigawatts, and it goes back to what I said right at the beginning. STEP is not designed to produce commercially viable electricity.
It's more like Hogger Hall.
It's a demonstration that one can produce industrial levels of power. What it has to do is demonstrate that pathway, the pathway to a commercially viable machine, and that would have the kind of. I was involved in the 1990s about looking at sort of commercial type spherical tokamak power plants. They were quite ambitious on the plasma physics, but we were looking at a more like a 50% return. So something like a 1.6, 1.7 gigawatts of fusion power giving you around gigawatt. No, it was more than that. 2 gigawatts fusion power giving you about 1 gigawatt electrical power. And so that's more what we would aim for the commercial power plant. That would be too ambitious, I think, for a 2040 target, and probably not appropriate because the cost would be higher. What we want to do is to demonstrate, for as low a capital cost as possible, the commercial viability, then go on and deliver plants that have that commercial viability. I don't think there will be 100 megawatts, no, because that's it'll be at the gigawatt scale. Fusion likes big, so it's likely to be at the gigawatt scale for the electricity generation. Yeah, likely to be. That's not necessarily a good thing. It's nice to have 100 megawatt levels, provided it's 100 megawatts from a 200 megawatt fusion power. But fusion that becomes more challenging to think. How does one do that with fusion? There may be a breakthrough that allows us to do that, but it gives you more flexibility if you can do that.
And if all the bits that we've been talking about today are proved to work, how big a deal do you think the scale-up would be to go from to that kind of machine?
That is an unknown question. I think if we knew that, we would know the answer to Ian's question. Is fusion possible?
Maybe I can talk a little about that, because it goes back to the pioneering nature of where we are. So we're putting materials into an environment that they have never experienced before. We are so far off our graphs that we have to have very large computers to even start thinking about extrapolating that far. Only by building and running machines such as STEP will we be able to put those materials and those systems and actually watch what they do and measure what they do. That's going to tell us what our actual failure mechanisms are. What thing we need to build big and which things we need to make thick, and which materials are great and which materials are not. And that will allow us to build the next machine so much easier. Just the actual switching on of STEP is such a big deal, and operating it, that I think we get sometimes a little bit too hung up on just how much we're going to produce. Just the switching it on, running in that environment and learning so much will make the next machine much easier and allow us, as we get bigger heat loads, into our 3 gigawatt fusion power machine. But we'll know which materials work in those situations and how they're likely to feel, so we can design them better.
And light a fire under the sector, right?
Yeah.
So it goes from being kind of like, the amounts of money that have been spent over the years in fusion are certainly not insignificant, but they're not, if you compare them to, like the Qatar World Cup, it's quite embarrassing in terms of what are our priorities as humanity. So, once we get something like this going, it really is about then setting the fire under, the kind of, the pioneers need to just get the ball rolling, and then it will gain the momentum.
Brilliant. Sorry, there was in the middle there. Have you got?
Peter Charlesworth, University of Oxford. I think for a lot of us who work in materials research and the things that you've just been talking about, it's interesting to have some clarity, because in the paper that is being released that we're talking about today, there was a liquid lithium blanket, and you've just said all of the other methods of producing tritium, which is something I myself am interested in. So from your perspective now, does that mean you're not set on one method of tritium producing? And if so, can you sort of outline what you're doing in order to test these things, and what is the scope for that?
Very happy to. So it goes back to, you saw a snapshot in time when we released the papers, and when do you release a paper? We've been going for 5 years, and boy, have we learned a lot and looked at an awful lot of different concepts. So that was, you can see all the trades and how we ended up with liquid lithium in that paper. We also, in the paper, explain a lot of the difficulties with that. You've got the tritium extraction piece, you've got the vanadium supply chain, etc. And so what we've done since then is we have looked back at lots of different other breeders, ones we'd thought about, discounted, brought them back in with new knowledge. We've got so much better modelling now, so much better knowledge about all the different types of breeder concepts and tritium extraction systems. So we're now in a process of reassessing. So lithium is still on the table, but we are getting much closer to reassessing and looking at what we're going to do. So that is the stage we are in, and getting a clear development plan for what happens next. So I think that's an honest answer for where we are.
Okay, yes.
Mohammed from Tokamak Energy. I wanted to see if you could talk about a little bit the nature of your challenges, emphasizing the spherical nature of STEP, and whether, how that's been challenging.
Yeah. Do you want me to do it, or do you want to do it? I'll do it. I'll do it. Yeah. Okay. So a spherical tokamak has a major issue when it comes to tritium breeding, that you have a very slender central column, and that means there is not room for breeding as well as shielding your magnets in the center there. So that means that you are left with just the outside, the outboard, to be able to put your blanket around to breed tritium. You've then got to, through that same area, get all your heating and current drives in there. You've got to put limiters in there for the plasma so that it doesn't destroy the first wall. And that leaves you with a certain amount of area that you have to breed tritium. For a spherical tokamak, that makes getting the same amount of tritium, to breed as much tritium as you burn, extremely difficult, because you've just got less area to breed with. And it means that there are some types of breeder and some types of breeder blanket that just aren't feasible for a spherical tokamak, at least at the moment, as we understand it with our current knowledge, that do work for a conventional aspect ratio tokamak. I don't know if there's anything else we ought to be saying at that point.
We probably shouldn't, because we do need
sorry,
to... No, that's fine. I think this last discussion actually really brings us very well to Debbie Kempton's. Now, yes, you're here, Debbie.
Yep, I am.
Is going to give us... yes, sorry, thank you very much to the panel. So, maturing the design. So, next steps.
Next steps, right. Right, so good afternoon, everyone. You'll be really pleased to know we are in the home stretch, and I hope you've enjoyed the earlier presentations and the panel discussions, and I hope it's become really obvious about how complexity, connectedness, and compromise are pretty much the watchwords for the program. For my session, I kind of thought about how I was going to fill 10 minutes. I thought I could speed read the paper, right? 10 pages, 10 minutes. It might be possible. Equally, if we were running really late, and I don't know if this counts as not, but if we were running really late, I could just say it's all a bit tricky and then bolt out and get some coffee and cake, because that would be nice for me. But instead, what I'll do is I'll take us back sort of up to the 100,000-foot level. And give some highlights from our paper on maturing the design. I'm not going to cover it in depth. We'll leave that as an exercise for the reader. But there's 3 things in particular, I think, that I would like to highlight from the paper. The first one is that to achieve maturity, we need to think about the plant in a holistic way. And you've heard a lot about all of the interconnectedness throughout the day. Second, we also have to use a combination of physical and in silico verification and validation methods. You can't test everything. And then finally, we need to think about maturity management in a slightly different way. So if I come on to the first part of that, from a holistic point of view, we obviously have to take into account the interconnectivity of the design, right? That's including all of our design drivers, and Chris touched on a load of those earlier, so did the rest of the team as we went through it. Changes in one area often have knock-on effects, sometimes unexpected effects, so that big picture view is really, really essential. But in addition to thinking about the design as a discrete task, we also have to consider the environment that we're operating in. It also materially impacts the design process and even some of the design choices we make. A good example of that is that we are developing a first of a kind, and we're working in an emergent environment, a VUCA environment, where that's volatile, uncertain, complex, and ambiguous. So traditional ways of working aren't always appropriate, and there's just no blueprint for how you get through it. And we have to plan to replan. And I won't say plan to fail, right? A lot of people like plan to fail, because I don't think in this context, something that doesn't work is a failure. It's a learning experience. And one that may provide useful information to other people trying to solve fusion. And I think, as Edison famously once said, as he was trying to invent the light bulb, he said, I have not failed 10,000 times. I've successfully found 10,000 ways that will not work. And I'm pretty sure it won't take us 10,000 goes, right? I'm not advocating that. But it's definitely not going to be a linear process. And when we think about that first-of-a-kind space, that also means that there is no established or mature supply chain for many of the key components or capabilities that we're going to need. So that means we need to upskill people and we need to develop new capabilities, but it also means that there's almost certainly going to be design trades for the prototype that may not reflect a final design for a commercial power plant, but that proves the concept and shows that route to commercialization, and that's what we literally just talked about. There's also the emergent regulatory environment to consider. So one where the practical applications of new legislation and all the stuff that Sally's working on are coalescing as the design develops. So as we learn together as regulators and designers and apply that legislation together, we may find ourselves needing to iterate the design. Now, so I know I said earlier that failure isn't bad, right? And that it's a learning experience. But there's perhaps one exception. We've got to consider cost, right? And again, we've literally just talked about that. We do genuinely fail if there's no route to a cost-effective solution. And how we think about the prototype is different from the commercialized solution. But that does put design to cost right at the heart of all the trades we do. And honestly, we've got to keep track of all of it. If we have disparate systems for designs and models and simulations and risk and decision making and trades and, that therein lies madness, right? You've got to be able to get your arms around all of it. So we're employing model-based systems engineering and a PLM system to enable us to have that holistic view and that integrated view of the design. And then finally, we need to think holistically about the how as much as the what we're going to do. So things like, how are we going to develop people? How are we going to create a culture of best for program? How are we going to develop new processes or tools or infrastructures, all the enablers that allows us to do the engineering? Those aspects have to mature alongside the design work. So in short, in sort of that holistic view piece, we've got to consider all aspects of the program, all the levers and drivers on the design, and they all have to move together, which is just another way of saying we have to kind of have balance in all things, and it's kind of rather Zen in a way. So maybe the next paper will be Zen in the art of fusion power plants. But seriously, taking the holistic view means that the plant and the people and the program will all work in harmony, ensuring that we do the right things at the right times for the right reasons. So our second, moving on to verification and validation, is sort of that second major challenge we have in maturing the design. We've got to create confidence in key technologies and processes. And I think we've talked about this already. The rub in all of this is a lot of the design just can't be fully validated until we build the full-scale plant, right? And a good example of that is plasma scenario, which we talked about earlier, but we've just talked about materials and some of that as well. That means we're running a parallel technology demonstration program alongside the design program. One that's going to rely heavily on that in silico qualification, so modeling and simulation, as well as the physical testing to build confidence to a level. And I deliberately say to a level because STEP will carry risk that we cannot fully mitigate right up until the day we turn on the lights. So how are we going to get there? Or in other words, how do we balance, that word again about balance, the need for confidence against the practical limitations of some of the physical testing. So we're going to do a couple things in that space. We're assessing the state of the design regularly, and we'll come on to that when we talk about maturity management in a minute. We are prioritizing technology demonstrations for key and critical systems. So the systems that define other systems, the things you have to set first, and then those specify what happens afterwards. So the good examples of those are plasma and confinement and breeding. Those are the defining systems. Oops, I'll go back. We are employing model-based systems engineering. That one's doing dual duty from helping us with a holistic view, but also helping us with verification and validation. That allows us to connect the various models and the simulations and the test programs to the design in a way that's meaningful. It is just too much stuff. It is too interconnected to try and manage it all separately. We're doing FMEA's failure analyses and doing them early, and we're doing them often to inform the technology demonstration program. That allows us to take a risk-based approach, one where we can use risk burn down as a way to inform the topics and the priorities for the technical demonstration program. And then equally realized risk, so something like we have a test or a simulation failure, also can inform the next step. So we're taking risk as a mechanism to inform the order in which we do things. And finally, we're moving in a really agile way. You know, we have an unequivocal readiness to discard a pathway when the journey appears to have reached its conclusion. If it's not working, we're done, we move on, right? That doesn't mean that we're done forever. We may come back to it at some point in time, but we need to move on and get on with it. Finally, I'll turn to maturity management. Remembering that STEP is a first of a kind, we're operating in that VUCA environment with a high degree of interconnectivity. So it's pretty easy to see that traditional maturity management techniques don't really work, or rather, maybe that they're necessary but not sufficient. So we needed to find a new way to determine what good looks like, a form of assessment that wouldn't allow the program to pass a maturity gate with sort of a rubbish design, and that does happen in the wide world of program delivery. You know, there's that old adage that you get what you measure, and we need to choose and measure our things wisely so we come up with the right answer at the right time. So we've developed a meaningful set of metrics to sort of strike that balance, again, the word around balance, between design, maturity, and risk. We're focusing on confidence, so that means maturity of understanding and maturity of methodology, but also completeness, the maturity of the design. We look at things like the volatility of the design, our uncertainty in the design, complexity and ambiguity, so that's our old friend VUCA coming back. And we've tailored those measures to the phases of the engineering life cycle with a clear definition of what good looks like at each one of them. And so I'll give a bit of an illustrative example in here. So in the preliminary design phase, we may say that we want to reach a certain level of confidence and a certain level of completeness. And we could measure completeness by saying we have all the level 1 and 2 requirements defined, or we have all of the interfaces defined. But just because they're defined, that doesn't mean they're any good. That doesn't mean they're appropriate. So then we could measure confidence in those definitions by how often our requirements change, how volatile is it. We could look at how much risk we're carrying against any given requirement, so how much uncertainty do we hold. We could look at how complex the design is, so the number of interfaces or requirements we have. Or we could look at how ambiguous it is, how many assumptions are we still carrying around. So that gives us a sense of how much confidence overall we can have in the design. Let's see, contrast that to a detailed design phase, where we'll have a higher target level of confidence and completeness, but we might look at things like the bill of materials or drawing completeness instead of requirements, or the amount of margin we have in a particular design rather than the number of assumptions. So what that means is we can look at a range of indicators that are relevant to the specific phase of the life cycle that we're in to understand design maturity. And even better, we can pull those indicators from our PLM system and use data science to give us a quantitative, not just a qualitative understanding of the progress, and more importantly, our confidence in the design going forward. So, to wrap all of this up, when we're maturing the design, there's not going to be a prescriptive or right way through it. It is an evolving and emerging undertaking. That's been the theme of the day. But it requires that holistic view of both the program and the product lifecycle to create the balanced outcome. So I'm going to leave you with this picture. And I like this image. I found it as a stock image. I felt like I got lucky. Not just because it's in the STEP color palette, but because it's balancing wildly diverse things in unusual axes. And that really kind of sums up STEP. That we're maturing the design by taking a holistic view across a wide range of many times seemingly unrelated topics to create a balance both in the product and the program. So that's it for me. Thank you very much.
And last of all, from Massachusetts, I think we should now have online Dennis Whyte. Yes, there you are. I think it's a very important element of this, the impact on industry. Please fire away with your experience. Can you hear us?
Okay, yes, sorry, I'm just having a hard time hearing you. Okay, hi, yeah, thank you for the invitation. So I just want to start, of course, with STEP is an extraordinarily exciting entry into the push and commercialization for commercial fusion. And it's going to obviously play a major role in the fusion industry, not just in the UK, but I believe in the worldwide effort. And I'll start with an interesting observation. Sometimes when I speak in public, people hear this word commercial and it triggers a mixed reaction. Like there's this mythology to fusion. Aren't we pursuing this new energy source to address our biggest, global problems like climate change? And, yes, we are. And the pursuit has been noble. And we also have to note, the sacrifices of our predecessors in spending their careers and understanding this, quite complex science of fusion. And thanks to them and other efforts which are underway right now, we're at a point where I think we can see our way to what it would look like. But as correctly pointed out in the introductory paper from now published in the Royal Society, that even if fusion development occurs at a national or global strategic importance, fusion power plants must be affordable to build, finance, and operate. Because if you don't achieve that, then fusion will not have the impact on the scales that we dream of. Because the science of fusion we've known for a long time tells us that it can really provide a large fraction of our energy needs so far into the future without the negative impacts of our present energy sources. So, this means we shouldn't also then underestimate the difficulty of this task of commercialization and the challenges that face a still nascent and exciting but nascent fusion industry. In a real sense, I would argue this realization is because now we know enough about fusion science and engineering that we can define those challenges. And also point out, in some sense, the context of this should be that we're not without insight or a history of other efforts where we've grown something that looks like a fusion industry with many impactful advances. You take a look at digital, biotech, things that have happened really within our lifetime. The solutions don't come as silver bullets. They come as coupled innovations brought together in a cohesive manner. In fact, my MIT colleague, Professor Angelou, and myself have an article coming out in Issues in a few days, which actually pulls out the similarities between the development of biotech and fusion, the challenges and opportunities. And turning to the papers that you've published, I really see it as a set of papers where we've heard much of the discussions, the complex set of trade-offs in design, function, and costs. And of course, the integration happens well past the science of making fusion happen. It's in all those technology of energy extraction, materials, component resilience, maintenance, electricity generation, and don't forget safety, very important for commercial's future. And the STEP papers indicate a conceptual design that can really pull all these together to succeed in its technical mission of putting fusion watts on the grid. But the papers also recognize the severe tensions in the design space. Is this the right size? How could it make more electrical power? What are the pros and cons of particular choices when it comes to cost effectiveness of such a prototype? And while all of these are significant, fusion poses challenges that are more than just technical. And we might call them structural organizational challenges, because these have also been hurdles which have been in front of technology development. So should we have a competitive or a collaborative environment? Should we have aggressive or conservative timelines? Or how about how aggressive we are on technology innovations? At what scale do we do this? Do we do it locally? Do we do it like in the size of a company? Do we do it nationally? Do it internationally? These decisions matter as much as the technical ones to make an entire industry. So with regards to STEP, besides just that it is a technical design, it's actually the construction, I would see, of a national framework which has been tailored to the very rich history and strengths of the UK fusion effort. And then one hopes a growing, thriving industry into the future. And seen through this lens, STEP is very much a framework for innovation So you have the sites on the game changer. The game changer in fusion will be watts on the grid. You know, in some sense, regardless of the cost that it's done at, that's going to be a milestone achievement. So you have assurances through a national program of achieving that core mission, but flexibility in the design. And I think this is where we have to be very cognizant. You know, just take a look at the last 4 to 5 years. If this is any indication, we should expect way more innovations and insights. Let's take a look in the last 4 to 5 years. Strong fusion self-heating in the National Ignition Facility, HTS performing magnets, you know, built by CFS, MIT, Tokamak Energy, and others at a scale necessary for fusion. Record fusion energy in jet. Jointed superconducting coils in the spark magnets. New regimes have improved heat performance in diverters, for example, for out of mass upgrade. Vastly improved simulation capability for plasmas. And then you think about high performance computing and things like machine learning and engineering design. These are being applied by my students, by our teams at places like MIT and Commonwealth. And much of these are now incorporated into the step design and also into like the device Spark, you know, that we're building with our CFS partners outside of Boston. Provide that key milestone, which is DT fusion power at high gain and self-heating at levels commensurate with commercial fusion. But even then, Spark does not, by design, put power on the grid. So if I look into my crystal ball, and some of it informed by our recent activities, there's going to be many more coupled disruptive advancements, in particularly, I think, in the energy extraction area, which has not actually had the focus of the plasma innovations, I would argue, in the last several decades. So what is this going to look like? I think it's going to arise from AI, material syntheses, rapid testing of new materials with new methods, what was just discussed previously, tritium production, where there's a lot of very interesting ways to get at it, RF source technologies, and as seen in the papers, providing a flexible but stable platform that can get you past the fusion milestones, but at the same time is not too rigid that it can't actually adapt itself into those choices. It is really an important one, because you still want this platform to be able to adapt actually to those. So this is the tension that is naturally there. And I'm personally fascinated by these challenges because I've been involved in a variety of different aspects of how this has come about. And we see really a variety of different models about how we imagine these disruptive new tech industries are made. We cannot deny the power of entrepreneurship and competition because it really spurs innovation. It's extremely powerful. But in fusion, when you look at the breadth of the needed science and engineering and organizational expertise, that it's a scale that seems to beg for shared resources. And what if in the end, we really shouldn't imagine like a single fusion concept getting there, but rather an array of fusion companies and concepts that meet the highly diverse energy demands of the world, because the energy market itself is not monolithic. Look at aviation. Airbus building an enormous passenger airplane, Cessna with a plane that can land on a lake, and Bell Helicopter. They all use exactly the same principles of flight, but they actually serve very different purposes in the marketplace. So it's really key in this because in the end, a government program alone is not, in fact, fabricated to make a competitive product. So this is the way that you have to see yourself. You have to be responsive to the market, not just the technology demands. And what I see in STEP is really a great candidate to tackle these tensions. The way I look at it, it's the use of a government agency and the stability that comes from that to set the framework and then leans into the private sector in a heavy way. And like in the technical choices in STEP, I think this is very much an organizational solution that tunes itself to the UK and other Commonwealth countries where things like crown corporations, which essentially describes what I just said, have delivered key tech and infrastructure sectors for multiple decades. So to conclude, and please excuse my American sports reference, this event is pivotal because now we have a major Western nation stepping up to the plate, pun intended, to commit to a development of commercial fusion. Making this a national imperative brings the financial, human, and organizational resources to bear. And on this effort, the UK AE team, the STEP team, and the entire UK government must be applauded by all in this. But the road ahead will continue to face challenges because the goal is not just a single device, but actually the development of the full commercial ecosystem. And this means there remain critical choices about the STEP program Its strategic, its place as a strategic development tool in terms of fusion. So again, congratulations on this. I think STEP provides a critical opportunity for UK fusion to move forward. I'm personally very much looking forward to seeing progress on this and collaborating with all of you to bring fusion energy one step closer. Thank you.
And then finally, we have, Paul Methven, sorry, Paul. As CEO of UK Fusion Industries, is that right?
Well,
this is,
UK
you're going to take it.
Industrial
You're going to take it forwards.
I'll take
it's
it
all
forward.
yours from here on to close. Thanks very much.
Thanks, Roland. Well, good afternoon, and what an afternoon, everybody. I'm going to start with the most important thing, which is a number of thank yous. So, firstly, a huge thank you to the Royal Society for agreeing to publish this special edition of Philosophical Transactions. It is a genuine milestone in the programme. We're hugely grateful for the opportunity to have done this and to put our work out in the public domain, to put our head above the parapet, actually. So thank you to the Royal Society as an institution and to the reviewers and the editorial team who've sweated for hours reading these papers and helping refine them. For the event today, thank you firstly to our comms team, who I think have done a fantastic job in putting all this together. It looks absolutely amazing, especially backed with the new brand, which everybody, I'm glad to say, is really enthused about. I certainly am. To the panels and to the speakers today, of course, many of whom authored papers, and to all those authors who didn't present today, I genuinely know, having felt your pain and done one of these things, that there's a huge amount of effort that's gone into it, a lot of toing and froing. It's really high quality, so thank you to all the panelists, speakers, and authors, and to Roland for comparing us today and getting the discussions going so well. And behind the scenes, I do want to call out three people, which is Stuart Muldrew, Rhiann Chapman, and Hanny Lux, who've been across every single paper in depth and done a lot of consistency checking. So for everybody that's been involved in this whole effort, can we just put our hands together and say thank you? So the package of papers that we've talked about today represents the STEP prototype plant at a point in the design process. And it's a point of, as you've heard, that we've already passed. We've already moved significantly on from that through the learning process. We are designing a machine and we're stimulating an industry, but first we're designing and building a capability to do all of that. A capability to design and deliver a fusion plant, and one that's absolutely honest, I hope you'll agree, having heard today's talks about the extent of the challenge and the balances that we have to consider. Nobody has yet solved the integrated challenge of fusion energy, including us in STEP. But the focus we're applying is refining and clarifying that challenge more and more each day. And the capability we are building is better able each day to work through those challenges. Now, some of those challenges are unique to the spherical tokamak, but by far the majority are actually common simply to any effort on fusion, and are driven by the scale of the plant, the scale of the power, the challenge of the materials, and every fusion endeavor is going to have to tackle most of the things that we've discussed, and it's going to face most of those challenges, and it's going to have to resolve them. So whilst there are some unique STEP features, actually most of what we're discussing is sector-wide. So we're not at, or indeed anywhere near the final destination. We're on a journey. We're on a quest. And there is enormous value in that journey, as well as incalculable value in the final destination. The capability we develop is of huge value, and fusion is a driving case that will push multiple technologies forward, and I think will produce and push multiple industries forward. And we see, as Dennis was indicating, industry as really an outcome of this program. We need to make sure that those outcomes and a whole range of wider benefits, including societal benefits, are pursued as well as that end goal of fusion. Because the end goal is still uncertain, and because we can't spend money for decades and not realize benefits for decades. We have to deliver near-term benefits as well as that huge and important goal in the future. But I'd argue that though that end goal is uncertain, perhaps we shouldn't doubt too much human ingenuity and human resilience. Truly transformative technologies do take time, and often those that champion them were doubted, even ridiculed. The light bulb, powered flight, automobiles, personal computers, space travel, and much more are all examples where early proponents were doubted. And today, and Dennis mentioned, we're only really getting started on the complexity of the human body and mind, the interactions between those, and the prospect of truly individual management of diet and of genuinely personalized medicine. All things that we're very far from a full understanding of, and yet we do not stop the quest because we don't have that full understanding. We keep at that quest because it matters. And if there is a need, and if there is a desire, I think we're a pretty capable species of finding a way. And there is a need for fusion, and I believe we are capable of finding a way if we focus, and if we drive, and if we work together. I often quote, and I'll make no apologies for it, because it really can't be put better, 3 elements of President Kennedy's famous lines from September 1962 on the endeavor of going to the moon, which, as you'll see, has stimulated and informed lots of our brand quite deliberately. So firstly, he said, and you all know this bit, we choose to go to the moon. We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. That's the ambition we need. Without ambition, no human endeavor is mobilized or striven for. But he went on, because that goal will serve to organize and measure the best of our energies and skills. That's the practical element. By attempting to do the hard things, you have to organize in every sense, design and people, and work together. And then he concluded, because that challenge is one we are willing to accept and one we are unwilling to postpone. And that is the need. That is the ultimate purpose that binds folk together and drives action. And in STEP, we have that purpose, helping tackle global heating and driving economic growth. We have the ambition that matches the purpose. And I believe we have the practical approach that could get us there. So thank you for joining us today to discuss just one step on this journey. Thank you.